Hello friends, let's discuss about the water quality standards under the aegis of chemical process utilities. Now we have in the previous lectures we have covered about the different type of water properties, and we gave a brief introduction that why these properties are essential. Maybe if we are using the water for the industrial purpose or household purpose. Then we had a discussion about the quality parameters especially applicable for the drinking waters like BOD, COD, pH, coloring compound, total solids, total dissolved solids, etc. Now in this particular chapter we are going to discuss about the various guidelines for standard water quality. We are going to discuss about the water quality requirements for industries. We will discuss about the water quality for various kind of effluents, especially the industrial water pollution. Then we will discuss about the indicators of water pollution. We will discuss about the water pollution from emission, effluents and solid waste disposal. Now let us talk about the guidelines for standard quality parameters. Now the different countries they do have different guidelines for drinking water quality. So especially when we talk about the availability and a requirement, then every country or sometimes even every state they do have various guidelines for the drinking water quality. So the number of parameters may be needed, and number of parameters for which the guidelines are prescribed, they are also differ from country to country, state to state, region to region. Now here you see that in this particular table we have discussed about the various parameters and the inland surface water or in the Environment Protection Rules 1986. Now say the biological oxygen demand BOD is referred as 30 milligram per liter. Similarly, the chemical oxygen demand it is referred as 250 milligram per liter. Then coloring compound, it must not have any noticeable colors, 15 as per BIS code ISI 2000. Then the pH of the solution must be maintained between 5.5 to 9, and turbidity should be 30, and TSS or total suspended solids, that should be 100, and that means they shall pass the 850 micron sieve. Total fixed solid TFS should not be there, total volatile solid should not be there, the chromium maybe 2.0, iron 3.0, nitrate 10, ammonical nitrogen, and that must be 50 milligram per liter, Zeldal nitrogen must be 100 milligram per liter, sulfide, this represents the sulfur, it should be 2.0 milligram per liter, and TRS, that is referred as the total residual chlorine, 1.0 milligram per liter, and total lead, it should be in a traceable amount, that should be 0.1 milligram per liter. Now when we talk about the water quality requirement for industries, so industrial water quality depends on types of industries. Every industry they may have different type of water requirement, different type of effluent, that is purely based on the industrial own specific use. So different countries have different guidelines for water quality requirement, as I discussed. This may be differ for industry to industry and other uses. Let us take an example that India has 5 water quality classes from A to E, and China has classes from 1 to 5. Now category E in the Indian standard and category 4 in the Chinese standard are meant for the industrial uses. Now here you see that a class A different we have depicted, and we have compared with China. In class A, that is referred as class 1 in Chinese criteria, the drinking water without conventional treatment but after disinfection, whereas in Chinese aspect the mainly applicable to the water from sources and the national nature reserves. Now if we talk about the class B in Indian context and the counterpart is class 2 in Chinese context, Now, in Indian criteria, the outdoor bathing, that is in the organized sector, and in Chinese context, the mainly applicable to first class of protected areas of centralized sources of drinking water, the protected areas for rare fish and the spawning fields or fish and shrimps. Then class C, the drinking water source after conventional treatment and disinfection. Now, if we talk about the counterpart at the Chinese context, this is mainly applicable to second class of protected areas for centralized sources of drinking water, protected areas for the common fish and swimming areas. In Indian context, if we talk about the class D, that is the propagation of wildlife and fisheries, and in class 4 of Chinese criteria, that is mainly applicable for industrial use and entertainment, which is not directly touched by human bodies. And in Indian context, we are having class E, which is attributed to irrigation, industrial cooling, controlled waste disposals, and in Chinese context, mainly applicable to the bodies of water for agricultural use and landscape requirement. Now, below E, in Indian context, not meeting of any of the A, B, C and D criteria, and there is no criteria available for Chinese classification. Now, modern water treatment technology makes it possible to adjust the quality of any raw water to meet the needs of any industrial use. The cost of purification of for very low quality water may be high, which may not be deterrent depending on the industry concerned. Guidelines for industrial water intake are not so restrictive except for the chemical, including pharmaceutical, food, beverages industries. Now, any single industry may have several different production units that require water for various qualities, including the housekeeping, etc. In cement industry, for example, along with the captive power plant, there may be several production units like cement grinding units, boilers, cooling towers, and water requirement will be for say boiler water, cooling water, water for drinking, water for sanitation and housekeeping, water for green belt development and firefighting. A single water treatment plant generally satisfies all these uses, but sometimes more than one treatment plant may be necessary. For some purpose, like if you say the firefighting, green belt development, the treatment may not be required at all, and or if required, then up to a very minute steps. Now, here you see that this particular table depicts the maximum concentration of constituents in raw water for various industrial operations. Now, if you see, there are various characteristics listed in column 1, that is silica, aluminum, iron, manganese, calcium, magnesium, ammonia, bicarbonate, sulfate, chloride, nitrate, etc. Now, here you see that in the first row, different type of the industries enlisted or different type of operation enlisted, like boiling water, boilers water, cooling water, textile plant, pulp and paper, chemical industries, petrochemical. And you see that if we take one example, that in silica, the maximum concentration attributed for the boiler water is 150 and a cooling water 50, and other they doesn't require apart from the pulp and paper. Similarly, the aluminum, iron for boiler water, it should be the maximum level of say 80, and for cooling water it should be 14, and textile plant very minimum quantity 0.3. Similarly, pulp and paper 2.6, 10 and 15. So, all these are the various maximum concentration of constituents for different operations. Now, if you take the example of bicarbonate, for boiler water it should be 600 milligram per liter, and cooling water it should be 600 milligram per liter. So all these industries, they are having different maximum concentrations based on their use, based on their treatment protocols. Now raw water, as we mentioned in the previous table, it is not at all usable unless it is properly treated to achieve the required quality of a specific use. Now the water quality requirement for point use in different type of industry is very specific. Now here you see again, when we talk about the maximum concentration of constituents at point of use in the industrial operation. Now if you see that in if we talk about the silica, in the boiler water it should not be more than 0.7 milligram per liter, and similarly if we talk about the textile plant, it should be 25 milligram per liter. Similarly, if randomly we pick the bicarbonate, the boiler water, the maximum concentration or desirable is 48 milligram per liter, whereas in cooling water you can have 600 milligram per liter. Similarly, if we take the alkalinity, that is 40 milligram per liter in the boiler water, 500 maximum concentration, 500 milligram per liter for the cooling water, and similarly for textile plant it is 200, pulp and paper 75, and if we take the petrochemical plant it is 85. Now when we are talking about the water quality for effluent, in almost all countries there are standard guidelines on the quality of water discharged by the various industries, and effluent is you can say a very addressable aspect for all kind of states, countries and industries. So water quality standards, especially those for drinking water, are set by the Indian Council of Medical Research, and this bear the close resemblance of World Health Organization standards. The discharge of industrial effluent is regulated by the Indian Standard Codes, and recently the water quality standard for coastal water marine outfall have also been specified. Now in addition to the general standards, certain specific standards have been developed for effluent discharges from industries such as iron, steel, aluminium, pulp and paper, oil refineries, petrochemicals and thermal power plants. There are various legislation they are attributed to control the water pollution, and some of them are like Water Prevention and Control of Pollution Act 1974. Now this act represented India's first attempt to comprehensively deal with environmental issues. Now the act prohibits the discharge of pollutant into water bodies beyond a given standard and lays down the penalties for non-compliances. Later on, after 14 years, this act was amended in 1988 to conform closely to the provision of EPA 1986. Now this also set up the CPCB, that is the Central Pollution Control Board, which lays down the standard for the prevention and control of water pollution. Similarly, all the state level, the state pollution control boards, they are functioning under the direction of CPCB and the state government jointly. Then another act, that is Water Prevention and Control of Pollution Cess Act in 1977. Now this act provides for levy or cess and collection of cess on water consumed by the industry and local authorities, and this was basically introduced to see the water depletion or lowering the water table. So it aims at augmenting the resources of the central and state boards for prevention and control of water pollution. Now following this act, the Water Prevention and Control Pollution Cess rule was formulated in 1978 for defining the standards and indications for the kind of and location of meters that every consumer of water is required to install. Then Environment Protection Act 1986 sometimes referred as EPA 1986. Now, this act is an umbrella legislation designed to provide a framework for the coordination of central and state authorities established under the Water Prevention and Control Act 1974 and Air Prevention and Control Act 1981. So, under this act, the central government is empowered to take measures necessary to protect and improve the quality of the environment by setting standards for emission and discharge, regulating the location of industries, management of hazardous wastes and protection of public health and welfare. Now, here you see that we have given a comparative table of quality guidelines of 7 major countries regarding the industrial effluents, and we have taken the countries in question: Uganda, South Africa, India, China, Brazil, Mexico and Canada. So, if you see that the maximum concentration of constituents at point of discharge in industrial operation. Now, if you see that for the sake of example, if we take the ammonia nitrogen in Uganda, it is 10 milligram per liter, whereas in India it is 50 milligram per liter, and in China it is 15 milligram per liter. If we take about the BOD 5 days BOD, in Uganda it is 50 milligram per liter, in Indian context it is 30 milligram per liter, and in China it is 20 milligram. And if we take the Mexico and Canada, Canada is a developed country, so 200 and 300 milligram per liter respectively. Similarly, if we take the chloride or chlorine, the total residual, that is a 500 in the Uganda, 1000 if we talk about the chloride in Indian context, 1000 milligram per liter, and 1 milligram per liter if we talk about the chlorine or the total residue. Now, again if we talk about the COD, in Indian context it is 250 milligram per liter, whereas if we talk about the Uganda it is 100 milligram per liter, and South Africa 30 milligram per liter, and in Chinese it is 100 milligram per liter. Similarly, if we talk about the dissolved oxygen, in South Africa it is 75. Now, if we take the lead, in Uganda 0.1, South Africa 0.1, Indian context 0.1, whereas in Brazil 1.5 and Mexico 1.5 and Canada 1. If we take oil and grease, it is 10 milligram per liter in Uganda, and Indian context it is 10 milligram per liter. Now, if we talk about the mercury, it is 0.01 milligram per liter in Uganda. South Africa, they are having the 0.02 milligram per liter, and in Indian context it is 0.01 milligram per liter, whereas in Brazil it is 1.5 milligram per liter. But if we talk about the Mexico and the Canada, it is 0.015 milligram per liter and 0.01 milligram per liter respectively. If we talk about the pH, it is 6 to 8 in Uganda, 5.5 to 9 in South Africa, 5.5 to 9 in Indian context, China 6 to 9, Brazil 6 to 10, and Mexico 5.5 to 10. And if we talk about the sulfate, it is 500 milligram per liter in Uganda, and Indian context is it is 1000 milligram per liter. So, when we talk about the industrial water pollution, this is basically caused in different ways, like disposal of wastewater, drained effluents, waste dumped by the industries in landfill sites near a water source, both surface and groundwater, and discharge from mines. Now, there may be certain reasons. One is the direct reason, that is the lack of awareness. Lack of awareness and inclination of industries to protect the environment is one of the main cause of dumping the waste into the natural system. The tendency to reduce cost in waste management, and sometimes the industries cut cost in the solid waste and effluent management to increase profit. Now, this calls us the indifference towards the nature comes from the profiteering tendency of industries, especially small establishments, because they are unable to bear the cost of effluent treatment. Another thing, important thing is that unplanned growth. In old industrial hubs, many small industries had grown up within a small area long before the public awakening or public awareness to the environment pollution. In such area of unplanned growth during the earlier development, there is not enough space available for the construction of effluent treatment plant. So they have to bear, they have to either discharge to the common effluent treatment plants or they have to discharge it to the sewage. Then technological drawback. The technologically drawback industries sometimes neither upgrade their old and energy intensive production machineries nor their old and inefficient ETP installation, thus contributing heavily to environment pollution. Then lack of maintenance. Now, due to proper maintenance of water treatment plants and ETP pipelines and conduits result in increased discharge pollution into the environment. Then policy and enforcement. Some countries lack properly defined water policies, while others have well defined water policies but no enforcement machinery. Both are problematic. Both problems amount to the same thing, that is called the water pollution. Then we are some industries or some companies or some countries, they are having improper corporate policy. The corporate policy itself may not include a waste disposal policy, and therefore management may be uninformed about the waste disposal. As a rule, absence of corporate policy and management for implementation is defining part of the industrial pollution scenario. There may be certain indirect reasons. That is, one reason is the lack of scientific knowledge. Environmental pollution as an unintended consequence is generally negative and result from system being more complex and interconnected than industry realizes. Industry need to educate themselves about the discharging into the recharging zone of an aquifer system, dumping waste in riparian zone, and landfill in an unconfined groundwater system, because the toxic component can leach out to the groundwater system. Another aspect is the natural disaster and system breakdown. The natural disaster like earthquakes or tsunamis can cause widespread water pollution through destruction of plant and factories. Now, here are various indicators for industrial water pollutions, like category 1, the temperature and dissolved oxygen and oxygen demand. The parameters are DO, COD, BOD. The indicators are rise in temperature lowers the DO level or dissolved oxygen level in water. Discharge from cooling tower increases the water temperature, because they are at a relatively high temperature. So, the temperature in the environment increases and lowers the dissolved oxygen level, affecting the metabolic process of aquatic life. Normal dissolved oxygen level in natural water is around 8 milligram per liter at 30 degrees Celsius. High dissolved oxygen level, this indicates the good health for ecosystem. Industrial waste discharge increases COD and BOD and decreases the dissolved oxygen of water required for the ecosystem. Now, second category is the conventional variables. The various parameters attributed to this are the pH, TDS, conductivity and salt system. Now, these are the physiochemical indicators. Elevated concentration of these indicators are clear pointers to pollution. Industrial waste and effluent discharge increase the concentration of both TDS, the total dissolved solid, and suspended solids. pH may either increase or decrease beyond the permissible limit. The third one is the nutrients, and indicators are nitrogen and phosphorus. The compounds of nitrogen and phosphorus are main indicator of the nutrients in water and are found as soluble and as well as suspended particles. Industrial waste from the fertilizer and petrochemical plants may increase nutrients that result in eutrophication. The fourth category, it is attributed to the metals like arsenic, iron, chromium, mercury, aluminum, etc. Now, metals are released into water both naturally and from anthropogenic activities. The elevated concentration of metal in water may indicate anthropogenic water pollution. Now, if the body of water is linked with the industrial or urban wastewater disposal system. Fifth category, that is attributed to the hydrocarbons, polycyclic aromatic hydrocarbons and naphthenic acids. Now, these two hydrocarbons are common indicators of pollution, and they are toxic in nature if present in high concentration. The sources of these pollutants are petrochemical industries, oil sand mines, and chemical and photographic industries. The sixth category, that is the industrial chemicals, polychlorinated biphenyl PCBs and dioxins, furans. Now, industrial chemicals include carbon-based and synthetic chemicals used in agro industries, pharmaceuticals, chemicals, other industries, and some of these industrial products are potentially toxic in nature. They are non-biodegradable, and they are the clear indicators of industrial pollution. Now, apart from this, there are certain biological indicators. The biological indicators are direct measurements of population and the health of fauna and flora in body of water or aquifer. The commonly used biological indicators are macroinvertebrates, fish diversity, benthic algal growth, and benthic oxygen demand. Now, industries emit particulate matters that go into the atmosphere and come down with rain. The volatile organic compounds, and sometimes referred as VOCs, and mercury are also atmospheric pollutants, and they are emitted by the industries. Oil refineries and industries that burn fossil fuel emit carbon dioxide and oxides of sulfur and nitrogen. Now, these gases reacts with the atmospheric water, turning it acidic, which comes down as acid rain, creating widespread corrosion and lowering the pH of bodies of water. The two strongly acid forming gases are sulfur dioxide and oxides of nitrogen. Now, sulfur dioxide in the gas phase reacts with the hydroxyl ion and form HOS2 like this, SO2 plus hydroxyl ion OH plus HOS2, which is followed by the oxidation. So, HOS2 plus O2, HO2 plus SO3. Now, sulfur trioxide in the presence of water forms the sulfuric acid. So, SO3 plus H2O, and that becomes the H2SO4. In similar way, we can see that the nitric oxide, it can react with the OH ion to form the nitric acid like this, NO2 plus OH ion and HNO3. So, you see that various industrial effluent contain many toxic substances like heavy metals, oil, greases, toxic chemicals, gases, pesticides, and so on. Now, when these pollutants come in contact with the natural ecosystem through the bodies of water such as sea, streams or groundwater, the natural water becomes contaminated, and then the water purification, water conditioning is always required. So, when the level of contamination rises above the permissible limit, it renders the ecosystem unsuitable for aquatic biodiversity or for human consumption. Now, here in this particular table you see that there are the direct water pollution from industrial liquid waste. Now, if you see that there we have enlisted various sectors like iron and steel, textile and leather, pulp and paper, petrochemical and refineries, chemicals and fertilizers. Now, if we talk about say iron and steel, the cause for this industrial pollution may be the fugitive emission from handling, crushing, loading, unloading, smelting, and major polluting processes are pig iron and steel manufacturing. So, apart from this, when these causes we are going to discuss, then let's discuss about the various pollutants. They are the high organic carbon, suspended solid, dissolved solids, cyanide, fluorides, COD, zinc, lead, chromium, cadmium, zinc, fluoride, and oil and greases. Now, if we talk about the pulp and paper, the cause is the pulping and bleaching. They are the major sources of pollutants. Now, paper machine, water flows, fiber, liquor spills, etc. And they can attribute to the volatile organic compound VOCs such as terpenes, alcohols, phenol, methanol, acetone, chloroform, methylethyl ketone, detergents, surfactants, dyes and pigments, acids and alkaline solutions, etc. Now, petrochemical and refineries, again, they are the major contributors towards the pollution, and the process wastewater, tankage wastewater, cooling tower blowdown, ballast water tank flow, etc. Now, they can increase the total suspended solids, heavy metals, ammonia, H2S, trace organics, BOD, COD, oil, phenolic compounds, etc. And if we take the chemicals and pharmaceuticals in generals, so chemical for washing, the cleaning of floors, chemical byproducts, they can attribute towards the pesticides, VOCs, arsenic, cadmium, cyanide, mercury, chromium, lead, organic chemicals, etc. Similarly, if we talk about say microelectronics mining, now here you see that the various causes like acid mine drainage, heavy metal contamination, leaching, processing of chemicals, erosion, sedimentations, and they may form the COD and organic chemicals from common metals like iron, aluminum to cadmium, selenium, etc. Now, if we take the food and beverage industries, again it's an, you can say, the upcoming field in respect to the chemical engineering. The causes the grey water from washing of raw food, cooking, additives, coloring, preservatives, decomposed food waste, etc. And they may, the pollutants are BOD, total suspended solid, excessive nutrients loading, nitrogen and phosphorus compound, pathogenic compounds, pathogenic organism, residual chlorine and pesticides level. Sometimes thermal energy is again the contributing sector. Basically attributed to the fossil fuel burning, and they may impart the fly ash, heavy metals, thermal pollution and acid rains. So, when we talk about the water pollution from solid waste disposal, the industrial solid waste is defined as the waste in solid form generated from industrial activities including manufacturing process, providing services to the various establishments, maintenance, etc. Now, here if we see that sometimes these industrial solid wastes are hazardous and sometimes they are non-hazardous. So, if we club or if we classify these two streams, like hazardous may include the medical waste, paint residue, fly ash, sludge, and waste is generally considered hazardous if it is harmful to human or environments. Now, non-hazardous it is attributed to the construction materials like metal scraps, and this can affect the drainage system and land use pattern. Now, if it affects the drainage system, again the growth of microorganisms and other decomposition may take place. So, it may become the non-hazardous operation may become the hazardous one. So, at last in this particular lecture we discussed about the various aspects of water quality assessment, and we discussed with reference to the various industries and various common industries, and we have already discussed or performed the comparison between India and China. Apart from this, in the different standards, we discussed the common parameters among different countries, and for your convenience we have enlisted the reference, and if you wish to have a further reading you can take the help of this particular reference. Thank you very much.